So this is the technology part of the breakout. You just kind of heard the overview of the Claremont locally grown power, and they're going to be talking about some of the economics that have to do with this thing. Before we actually get into it, and my contact information will be on the end as well, I just wanted to ask a question that we're going to get to right away, but it goes to something about solar, that although the cell was invented in 1941 and subject to the 1921 Nobel Prize for Physics for Albert Einstein, it's a pretty simple question, because we're going to see some mayhem in a minute. You put a solar panel in the sun, and we let everything settle out. And then we have an inverter that's connected to the grid, and we switch the inverter on. So I'm going to just ask for a show of hands in a second. So the question is, does the solar panel get hotter, cooler, or stay the same? How many people think hotter? Okay. How many people think cooler? Okay. And how many people think it doesn't change? Okay. That's interesting. There are actually two big myths about solar. The first one is that it gets hot in the sun, and the second one is it gets cold in the shade. It'll actually be obvious in a second, but you know, we're all STEM in one way or another, and we get captivated by that. And just so that we're all in good company, a person who is very high ranking in California's energy policy had a solar panel that burned a hole through itself in the Altiplano of Peru, where the median temperature is 4 degrees C. And he thought it was because it gets hot in the sun. So, common thing. Let's get to it. So here's a thermograph of a house with a solar array. And the key behind this is this idea of conservation of energy. It applies to everything. All the energy flows have to equal zero. What goes in has to come out in all forms. You can't have anything added or anything taken away. So when you do the arithmetic, it's all got a balance. So if we take this array and we drop 1,000 watts per square meter of sunlight on it, and then take away 200 watts, it doesn't have 1,000 watts anymore to dissipate as heat or as a reflection. There's only 800 watts left, some of which goes off in reflection, and the rest is dissipated as heat. So in an experiment that is going to be recreated in your physics department, you're going to actually do this. Take a solar cell, an individual one, expose it to sunlight, or expose it to sunlight equivalent, have it open circuit, tune it to its maximum power point, so you're extracting energy from it, and then tune it to 0 volts where there's no energy extracted, but it's heavily loaded. And you'll actually see that the minimum temperature will occur at the point where it's producing the most power. First law of thermodynamics, it doesn't have a choice. But what that means is that solar panels are really cool. And when Einstein came up with this law of photoelectricity, he only really conceived of the fact that we're going to capture photons and emit photoelectrons. And so the concept that it actually was going to get hotter somehow wasn't there. So if we look at this thermograph, the array, which is getting the same light angle and power as the composite roof in this house, actually is considerably cooler than the surrounding roof structure. Okay, so take energy out of a solar panel, it will cool. Well, if that's true, then why do we have such stuff going on in terms of materials? There is a huge multi-million-dollar project going on at the Stanford Linear Accelerator Lab in my part of the state, just to look at solar materials to make them more robust for this horrible heat problem we have with solar. And it is a horrible heat problem. This is a tracking array that's in Spain. We see these little bright spots. If we're standing back from it, we get closer to a different solar panel, and we can see these are actually individual cells. These hotspots are not the result of defects. There's two different kinds of hotspots. This is the kind that happens from photocurrent. They're the result of choices that an inverter made. And when I click this, what you're going to see is the evolution of a hotspot. So what we're doing, and this is in real-time thermal image, is we're taking a cell that was in production and then at 0.8 of a sun, and we are acting as if the inverter that was associated with it said, hey, I've got 20 cells here on one panel out of 12 times 60. The better choice with 20, rather than losing 20% of the energy for the whole array is to bypass this one by pulling the voltage down. And so what we're looking at with all this heat isn't what came from the sun. It's actually the electrical power dissipated in this cell from the other cells in the solar panel. So solar cells get really hot in solar panels because they're forced to dissipate power from the other cells, not from the sun. In fact, there's only 25 watts available in sunlight to a 156 millimeter square cell. So there just isn't that much power available. You have to take the electrical power from the surrounding cells to do this. Now, the other thing I want to call your attention to is something weird is happening. See how these metal stripes, they look cooler. That one's cooler than those two. These are the contacts that take the power back out of the cell. These two are merging with this very hot background. Oh, by the way, the little dots are my thermal imager saturating because it can't handle the difference between room temperature in one corner and how hot this cell is becoming. So these temperatures are actually significantly lower than the cell is achieving. It's because I'm forcing it to continue to document the background temperature. But just to give you an idea of how hot this went, so way, way hotter than what you need to cook an egg with. In fact, the kinds of characteristics of the glass on a solar panel really resemble the properties of ceramic cooktops on stoves, where you have these extreme temperatures over just a few millimeters of distance. Okay, so what happened? So this is this cell afterwards, and those are those two interconnects that you saw fading. What happened was that as it heated, the cell went one direction, the metal went the other in terms of thermal coefficient of expansion. It buckled. We exceeded the melting point of the solder. It unsoldered, and then this was kind of cool. I don't know if I could do that again on purpose. That's actually a column of solder that formed in its molten state, and then as the cell cooled, the solder locked the metal into its deformed position. Okay, so that's a laboratory experiment with just a cell, just the metal, just illumination. Believe it or not, I can't find this in the literature. There's a paper up here, which is the basis of what you guys are going to be doing, and these are all handouts for you guys. But this is what it looks like outside the solar panel. This is what it looks like inside the solar panel. So this is actually a cell that was taken from that array in Spain and then taken apart, and what they noticed was, wow, the solder's decomposed. This is the back side, that's the front. And what happened was it's all mashed together, laminated together. It went through many cycles and evolutions. The solder, which is basically came apart into its individual grains of material and decomposed, and ultimately the connection failed. Okay, so that's bad. That's the choice the inverter makes. So this is why we have so much research into materials, the interconnects, the quality of the solder, all that stuff. Well, this is what happens if you actually have an interconnect failure under load. So this is courtesy of University of New South Wales. In that first instant, when the interconnect opens and current is flowing, and that first micron scale gap, we're going to exceed the insulation capacity of the nitrogen in the air. In fact, we're going to actually pull electrons off of the nitrogen and form a little tiny microplasma. Now, that'd be okay if this was like a battery, and as it burned away a little bit, then the current would fall and there wouldn't be enough energy to sustain it. Unfortunately, the photoelectric effect is, flux in, current electrons out. So cells are extremely rapid in terms of their voltage response. So what happens is as it began to consume the solar cells and the arc became larger and larger and larger, it fed more and more voltage in, maintaining a constant power density, so it actually maintained the plasma. It's pretty staggering what we were looking at. You can't deal with this if it happens. That's why there's so much work in materials to prevent this from ever occurring. because nitrogen plasma is really hot. We don't have any hope of making anything fireproof. And it would seem to be an inevitable risk factor with solar because of how solar cells capture photons and give you electrons. It's going to put out a constant current. The voltage is going to move around very rapidly. There's not very much capacitance. So you just have to stop this from happening in the first place. Guess what? We're not always successful. And when that happens, it doesn't matter if it's a tile roof underneath. If these materials come in contact with building structure, then you got a problem. And the converse is true. You can start a fire underneath a solar panel, cause it to decompose, the connections to break while producing power, and it will start a plasma and then spread the fire. So it doesn't matter whether the panel was the problem or the structure was the problem. You've got a fundamental issue. Here, notice the snow. And a unfortunate side effect of silicon diodes is that their voltages their forward voltages increase with falling temperature. So the highest voltages and the biggest risk for this sort of thing actually happen when they're cold. Counterintuitive when you're worried about fires. And there's another problem. So this is a 300,000 square foot facility. Notice this white area of the roof. You can actually see that when the early stages of this happened, it actually burned away the panels, leaving the roof untouched. Eventually it penetrated. But something else that's missing. What's not in this picture? There's no firefighters in this picture. Because as long as the sun shines, you get electrons. So there's no way to turn this off. It's not a good environment for swinging an axe in boots with water. So actually what you're looking at is a defensive posture. So that's the other thing, would seem to be an inevitable thing about solar, essentially drive us to higher and higher quality and details. And we're going to talk about the details of the design. So most of the time, first of all, most of the time it burns a little pinhole in the cell and nobody knows. Sometimes the cell fails. Most of the time when you have a plasma condition, it actually takes the panel, and you can see here the progressive fault. It actually chewed up the panel, got onto the wiring. Again, because we're so hot, we're going to take all the ULB0 materials and melt them away, and we're going to end up with this traveling arc. And then it just chewed up each panel in succession. That's a very common signature that we see, but the roof underneath is intact. In this case, this is a house with a composite roof, and as before, this is actually from a firefighting manual. This team, I believe, was in Maryland. You can't attack it while it's happening because you're putting yourself at risk. And really, even after this is all taken apart, the individual pieces of solar panel that are still hooked up are energized. There's no way to turn it off. And then it does get into the structures. Famous fire in Bernstadt took out something about the size of a city block in Germany. And this is what's left of that warehouse. They never rebuilt it. Was a total loss. And the decision was life over property for the firefighting teams. So this is just something that we're living with in solar, except it may be unacceptable. Okay, so that's the mayhem part. If you guys are expecting me to actually catch stuff on fire, wait a little while. Once we actually build some of the test setups with full-size panels, we are going to make fires, but not today in the classroom. So critical safety design parameters. First of all, on safety, there's voltage, current, and the matching of the power current between the cells. These all end up being critical. Unlike other building materials, you really have to sweat the details. Then we have energy yield kinds of things. So variation in maximum power voltage. It's very temperature sensitive and interacts with the grid. The peak power that the inverter can be subjected to and the limits of that equipment. And then wiring plant IR²R losses. Okay, let's just take these one at a time. So the first thing that we run into is that in the United States, for residential applications, the maximum system voltage is about 600 volts. And because of the temperature sensitivity of the silicon, you have to try to figure out what the highest possible voltage is under the most anomalous weather conditions that you could possibly have. Generally, a generally safe practice is to allow a 30% margin. So that means we only get to put 12 solar panels in series, about 3 kilowatts, and that's a number that you'll see in a lot of sites that get installed. And ironically, the more efficient and high voltage the panel, the fewer you can put into a string because of this problem. Standard panels are just cells and wires. So whatever the characteristics of the silicon itself are, the solar panel has the same characteristic, just multiplied by however many cells are in it. So the other thing that's nerve-wracking about this is not only do you have to try to see into the future what the coldest possible temperature at the site's going to be, you also have to try to figure out how the process variation is going to be on the solar panels that you actually get delivered, because this characteristic depends on the doping levels, defect densities. It's not a guaranteed maximum spec, so you end up with pretty wide margins from a design point of view. Solar is super unforgiving of arcs. I think this is really important. You're up against the fundamental physics of the device when you try to put out that plasma arc. It will fight you. Go ahead.
So I understand, like, once the arc happens, why it can spread, because there's no because electrons are still coming out. But how would the arcs? I know you probably talked about it, but how would the arcs start in the first place? Like,
so what happens is, if you've got a circuit that's carrying current, any circuit,
yeah.
At the first instant as you separate that contact, at one point you will have a gap that is so small that whatever voltage you have applied exceeds the breakdown of the nitrogen in the air.
Yeah. But how does that separation happen? Because of rising temperature?
So what we saw in the first place was the solar cell desoldered its own interconnects because it overheated. And then in the second case, we saw one that had gone through successive cycles over years of cycling temperature, and the solder decomposed.
Yeah.
The other thing that can happen is you can develop microcracks due to extreme temperature because of the differential coefficient of expansion between the metal and the silicon itself. And those cracks can end up in the wrong place and interrupt the circuit. So there's actually a whole variety of ways, all of which have to deal with evolving it under the kinds of temperatures that you guys just saw.
And so that differential heating that happens in the cells is due to the inverter?
So the differential heating is, the easiest way to visualize what's going on is imagine you've got a stack of batteries, chemical batteries, and one of those batteries is capable of carrying less current than the others. If you ask for more current than the weakest battery, so you make the resistor across that stack smaller and smaller and smaller, at some point that electrochemistry of the weak cell can't do it. The other cells stay put, and in order for everything to complete, you end up electrically reversing that cell. And we know that as the goo comes out and everything turns white and you throw the device away. But so the same thing happens with solar cells. They're all in series. So if you do something like partially obscure a cell with dirt, or it's a little bit weaker, or it's a little bit different temperature, or there's a bird that is standing on it, or a bird that flew by and left something on it, and it's partially obscured, it can't make enough photocurrent to match the rest of the cells. So if you left that unchecked, that would actually reduce the current for all the solar array, because all the current for all the solar panels have to flow through that cell. And so what the industry did to deal with that is every 20 cells or so, we put a diode in. And when the inverter does its sweeps, basically changing the load across the panel, it looks for the maximum power. And it might pull the voltage down, so ask for more and more current to the point where this weak cell in this string flips over, the other 19 cells are powering it backwards. That's what you actually saw in that picture when it got so hot. So it's burning essentially 20 cells worth of power in that one cell, not on purpose. It's just how we managed to not have that cell degrade the performance of the whole array in today's solar designs. And it's just kind of something that happens because of maintenance, because of the design and implementation. Of course, the other thing that can happen, pinholes, or because it got cold, you actually increase the voltage of the system above the insulation ratings without opening the circuit. The arc forms. Once it does, you get the same result. So several different ways, but we think of solar as being a very benign thing. It is if you do it exactly right, but otherwise it can be very unforgiving. So I'm glad you get this part, because this is something people don't think about. I mean, if you do an experiment and you run a signal to a solar cell and you move it around its operating point where its current is relatively constant, it is a super high impedance, almost no conductance. You can move that thing around, and that's what it does. Is that arc is moving around like this, and the voltage is going up and down. It's maintaining a constant power density with an unfortunate accident of physics. Okay, so voltage is a big deal. So the thing you want to take away from this is if you're designing a solar array, you look at what's printed on the back of the cells. You take that and assume it's going to be 30% higher than what it's printed to be, an open circuit. You divide that into 600 volts, and that's how many solar panels you can put into a design like that safely. 2, when is one sun not one sun? When you have ice crystals, when you have cumulus clouds. In this case, this is a sundog. It's a relatively rare event that happens by upper atmosphere ice crystals. Actually, there are cases where there have been 3 of these things. And yeah, it's really bright. And when you go outside on a day when you have cumulus clouds, and you can see the sun and the clouds are super white, and you think you just came out of a movie theater because it's so bright. No, it's really bright. If you take something out and measure the solar flux, you've got a really bright event. Why does that matter? Because the solar cell doesn't know. It's not actually regulated. Whatever flux is falling on it, unless the load conditions are changed, it will make that current. And it will do it very fast in these atmospheric conditions, as you probably have seen, in the spring and fall. They come on extremely quickly. So you've got to allow for that. That means that the wiring in the plant has to be able to handle at least 25% more current than what the solar panel has printed on it. And people can make an argument, depending on what kind of atmospherics you have, it should be even higher than that. Because if you end up exceeding even the current rating of one connector, once that connection fails, what are we going to have? We're going to have a plasma arc here, even though it's powered by the cells. So 25% margin on current over what it says on the solar panel. Super unforgiving. Basically, it responds in an instant. There's no ramp up or ramp down time. You put more photons in, you get more electrons out now. And any connection anywhere in the array can result in plasma. By the way, this is a common thing that happens to installers. That's why we have these fancy special keys and stuff, because you can actually do this to yourself by opening the circuit, like unplugging it from the inverter while it's running, or trying to unplug a solar panel while the whole thing's illuminated. Technically, you're supposed to cover it all with blankets and then pop this out when there's no current flowing because of this. Okay. Maximum power current. Matching maximum power current. As cool as it would be to be able to go buy panels and mix and match them, can't do it. The reason you can't do it is because the inverter doesn't know, it's just trying to find maximum power. And so if you have a panel that's 9% lower than the other panels, for whatever reason it is, actually that whole panel is going to get reverse biased, and 3 of the cells will go into hotspot. 9%. One cell, it takes about 3%, where the trade-off for 12 panels between one cell on a 60-cell panel against the entire array current. And think about that. That's a 0.2 of an inch shadow. That's the width of your thumbnail. So when you look at these arrays where nobody's cleaned it for 2 years and there's a band of dirt, you want to hope that that's actually consistent across the panels. This is probably a point where I should interject something about lifetimes. We talk about lifetimes in solar being 25 years and that sort of thing. No solar panel manufacturer rates the lifetime with a hotspot. So we just saw over 100 degrees C rise. The standard rate of decay of lifetime of an electronic device is that its lifetime halves for every 10 degrees C rise. So I won't make you do it. If something was rated at 25 years, and you take it 100 degrees C hotter, it's going to last 9 days. It's 1,000 times factor on aging. So once you've actually left a solar panel in this circular hotspot thing, if it doesn't desolder itself and fall apart, you'll actually move the dopants around in the cell and permanently damage its capacity so that even when you clean it, it won't be right.
So I know how it says here that the inverter only optimized for array power. But what if you had something with really high impedance connected to each of the cells so that you could somehow sense like when the cell is undergoing like the effect that you were talking about before?
What's your name?
Theasius.
Theasius? Yashis.
Yeah.
Yashis, very excellent question, and you're on the track. People have been trying to figure out how to prevent or detect hotspots for quite a while. That's a big deal. Early on, the people had the idea we would put like a protection diode across every cell. In fact, today with triple junction cells, they break down at such a low voltage you would do that. If you take the DSSC cells that are done here at Harvey Mudd, their breakdowns are 1.3 volts. You would actually have to do that on those cells. On SIG cells, they need a diode every 4. Detection becomes a terrible engineering problem because of the complexity of manufacturing a panel with all the sensors and stuff. And so theoretically, you could get in there and try to measure all that stuff. But if you wanted to manufacture this at some kind of a cost that would allow us to do mass carbon mitigation, nobody's figured out how to do that. And good news is you don't have to. But you're on the right track. I actually went through the evolution of thought that on the track exactly that you're on. Okay. Let's talk about another one. Plus or minus 30% for maximum power. So we got to match them. Unfortunately, the temperature coefficient of that voltage at which the maximum power occurs, it has the same temperature coefficient characteristic as a forward bias of the diode. It's actually related to it. Well, that sucks because now we've got to design our inverter to handle this very wide range, 480 to 235 volts, and it's worse than you think. The constraint here, of course, is the heat. Because the voltage is falling and the current remaining constant, the power is going down at 0.5%. We've got inverter specifications where if you get outside of what the inverter needs to produce power, it will curtail the power because it needs to have enough voltage to reconstruct the sine wave. And then we've got another problem that gets thrown in by our grid managers. Everybody in here probably walked in with an assumption that the utilities regulate the grid. That isn't really true. In fact, the feeder lines and the lines into your home, those actually aren't regulated. They just modify the settings at the substation. Those things are miles long, and they have enormous amounts of inductance. So they have quite a wide range of voltages that you can have. If you go over the entire ANSI specs, actually 240 volts can be as high as 252 volts, which would require 356 volts for a conventional buck converter to make the sine wave. Can you see the problem? So it's actually pretty tough to get the inverter to give you full power from the array over the entire range of voltages that you'll have to have when you take the grid and the variation due to weather conditions of the solar panel. There's a thing called CVR. If you're in Washington State or Tennessee, you're in luck. That's voltage regulation technology for feeders. If you're in California, they only got 13, and they're all in Northern California. So unless you're going to De Anza Community College or live in San Ramon, sorry, you're not regulated. So you're stuck with this larger range and the curtailment. It's tempting. We'll just put more panels on. Unfortunately, when we get to 18 panels, which guarantees that we can construct the sine wave under all conditions, now we get 900 volts open circuit. So it's great until it gets cold and then it blows up. So we end up actually designing these systems knowing that it's not going to actually be able to hit full power when it's hot. That really sucks, right? August, the sun's shining, and yeah, it's curtailed. Go ahead.
I was just going to say, CVR stands for continuously variable?
No, it stands for conservation voltage reduction. The reason they named it that is because V squared over R. So if you allow a residence to go from 114 to 126, that's a big delta V, and the power consumption of the household varies over a large range, as does the parasitic power on the transformers and every other piece of equipment. And so CVR is basically just static VAR compensation capacitors on the grid that react to the exact instantaneous conditions. Important point here, you don't have things like that in Hawaii. That's where they actually do allocation on solar installations, because too many solar installations in a small space result in too high a feeder voltage, and you can't maintain the ANSI standards. So HEI, Hawaii's utilities answer to that is we do a voltage study and your permit's denied. Of course, the technology's 30 years old and has been deployed widely in a bunch of other states, but that's for another session.
Are CVRs just very expensive to implement?
No. I'm part of a study with UCLA, and so I actually did the research to support that study. In Claremont, I think it came out to about $5 a customer. It's actually works out to about 8,000 metric tons per $1 million expended, which is better than an LED light bulb. The problem is you can't buy it because the equipment, however inexpensive it might be, there are things that go on the pole transformers. Actually, they're regulators that attach the equipment that are already there. That's Southern California Edison territory, not you. So you can't buy it, but it does increase the power consumption in your house and impair the efficiency of your solar array. And sadly, if you have a lot of people with solar arrays, the neighbors have higher voltages, service voltages too, and that causes them to actually burn extra power. So there's all kinds of good reasons why we should have that, but I don't want to derail this. Maybe we'll come back and do another one on the electrical engineering aspects of mass distributed energy resources. But know that even at the solar panel level, we actually have an interaction between the thermal characteristics of the cells, the design of the inverter, and the way the grid is managed that affect how much power you can get out of your solar array. Okay, so basically, we look at this, we run the numbers, we realize curtailment's going to happen, and we eat it because the other alternative is not acceptable. So you go to safety, and that means less solar production. Okay, peak inverter power. This is where that trifecta happens. All the panels have to match. They all have to be pointed the same direction at the exact same angle, because if you've got anybody who's off at another angle or partially shaded or dirty, what's the inverter going to do? It's going to cause a hotspot to form. Unfortunately, that means that all the power peaks happen simultaneously, and that weird 1 in a million atmospheric effect affects all the panels at exactly the same moment. So you end up stacking up all this stuff. And some of it's logical. For example, on a frosty day, the voltage is going to be higher, the power output of the array can be higher, and you've got an indirect reflection. It only lasted an hour, but it can be a big deal. So you end up stacking up these numbers. You end up with 60% higher power peak than the STC on the module. So that's a considerable margin in terms of the inverter sizing. Most inverters have power limiters, but they're slow. And so it's a race between whether or not the inverter overheats locally in its IGBTs and its internal circuits and fails, or it protects itself in time. So a 3 kilowatt array can actually peak at over 4.8 kilowatts for a short time under the right set of circumstances. And because we can't control those circumstances, we have to assume that they could all potentially happen at the same time. Okay, now we get to nice to haves. So all that stuff we just talked about, that was mostly about safety and reliability of the system. Here's an unfortunate fact of materials. Copper has a positive TC, and the power output as voltage from the solar cell decreases by 0.5%. The current remains constant. That sucks. So we get the entire power loss of the resistance, and we get the power loss of the panel at the same time. There's an amazing amount of copper. Because you look at the network, right? It has to cross the panel back and forth, and then you got 6 feet of wires, and then they're all stacked, and then you got a return line. There's over 500 feet of copper in 12 panels plus an inverter. And you got to count the windings on the coils in the inverter too, because all that stuff has that TC. So system efficiency degradation is compounded by all this. If you can hold it down to 2 ohms, which is a challenge, really big wire, that is a loss ranging from 4 to 4.8% over 20 to 40 degrees C. Okay. So we just went over these key parameters for safety. Voltage, 30% margin. Current, 20% margin. Power, 60% margin. The modules have to match. You better maintain the array. So if they're dirty, they better be dirty the same way. Otherwise, they need to be clean. Leaving a Frisbee for 2 weeks actually could end up shortening the life of at least that panel that's affected. It's amazing how quickly these things can degrade if you force them to do that thermal excursion every single day. I don't know, do we do material sciences, fatigue studies and stuff like that here? And yeah, okay. Yeah.
It's like a very short introduction to it, but people who actually
Yeah.
research computer science may do more of it.
If you guys are interested, just send me an email. I actually have studies on the degradation of solder, how solder decomposes over thermal cycling and stuff. It's really eye-opening. You do not want to do thermal cycling on something. Okay, so we've got these basic things. So you should be able to walk out of this, look at a solar panel and say, if I'm going to size this for somebody, I know what to do to be conservative so that this isn't going to cause a problem in the future after it's installed. Okay. Now we're going to play a thought game. So that other part was depressing, kind of. Mayhem, sweat the details. This is a thought experiment. What if we could engineer out the root cause? We don't know exactly what it is yet, but let's just think about it. So first of all, we want the solar panel to have a stable voltage over temperature. That really sucks that it has such a big temperature coefficient. It's a safety problem, and it's also a problem when we get into these situations of compensating copper. So we want it to have a stable voltage. We don't want that thing to have a tempco at all. We can't fight the fact that the voltage across the diode is going to fall. Its power is going to fall as it gets hot. But we actually want that to be expressed as current. Yeah, I know we're inventing a new material now, but if we got to deal with the fact that we're going to lose power, we want it to be current because that's going to operate in opposition to that resistive problem with the copper that has to conduct it. And it'd be great if it had a fixed upper limit. So if there's that bright thing that happens, the solar panel would actually regulate that out so that it never got to the rest of the system. And it's right there where the problem happens, so it could react to that potentially. And, wow, if somehow, when that arc began to open, the current fell, instead of remaining constant, the power density on the arc would decrease and it'd go out. So then we wouldn't actually be able to sustain a plasma arc. So with this one little thing, we don't actually have the ignition source for starting or propagating a fire on solar panels and structures. So that's cool. We'll include that in our thought experiment for this ideal panel. And then, because we would like to be able to carry this up to the roof and work on it without worrying that we'll actually, kill ourselves, or be able to unplug it when it's running without actually having it turn into a fireworks show, we'd really like the voltage to be driven low when there's no inverter. So if we handle this thing and it's not hooked up, it's benign. If we swing an axe and cut the wires and it's separated, it's benign. If you turn the switch off, it becomes benign. That changes the whole environment of firefighting around solar. So we do these things, and we'd actually have something that would be a consumer technology at scale that you could really begin to deploy like a roofing material. Okay, what happens to the design? Well, with a fixed voltage, even if we left the maximum the same, we get 16 panels, 33% more on each string. The copper losses would actually be almost perfectly compensated, so we get down to a 2.2% balance of system loss. Falling current extinguishes the plasma, and this low voltage, when it's disconnected, protects the first responders. All right, what caused us to get into this thing? Is there a root cause? Yeah, the hotspots that we said were kind of unavoidable in the beginning. Maybe not. Maybe we can engineer those out. So here's the fundamental principle that's at play with a solution to this. And we'll kind of let it soak in for a second. So as the voltage across the cell becomes more negative, its dynamic conductance falls. Well, okay, obviously true, right? It's the diode law stated as conductance instead of impedance. So that's cool. And didn't people know about that? Actually, Orr, who invented this thing in 1941, plotted the change in impedance with voltage across the cells, but didn't invert it. So he only saw it that way. Why does it matter? Because an impedance goes towards infinity, which is really difficult to engineer. But a conductance goes towards zero. Zero is the ultimate in a limit. So let's see how we can apply this to a solar panel. If we look at it as a series of conductances, conductances sum as the summation of the reciprocals of the conductances. Do a little limit theory. So if we take any one of these conductances and make it propagate towards zero, then the denominator tends towards infinity. The whole panel goes to zero. So we can actually sense the dynamic conductance of the entire solar panel, and by evaluating that, we can tell if any cell is experiencing a low voltage. And we can actually change the load conditions just looking at those two wires before any cell actually becomes reverse biased. So with this tool, we just apply it to the control law of a DC to DC converter that we make stand between the solar panel and the inverter and the rest of the solar array. And we get an ideal PV. So it presents an idealized panel with all those characteristics because what? We can do that with a microcontroller now. We can regulate the voltage. We can turn the power loss into a decaying current. We can use a, for example, zero current switching converter that has no energy storage in its inductors, so that if the voltage instantaneously increases, the current falls because we starve the inductor. So we can actually engineer all that stuff that we had on the wish list for the inverter, and we can provide an ideal load to the cells so that the cells will never experience reverse bias. And now we get to make dramatic changes to the design of the solar panel itself, starting with, instead of being forced to do this at 10 amps, or actually 8 amps, where any interconnect failure on any one of these things is catastrophic because the other ones are overcurrent, we get to cut it in a quarter and put 240 of these. So 60 of these, no, 240 of these. Why does that matter? Because resistance is a squared law loss, right? So 35 volts, maybe 120 volts, silver-coated copper interconnects, aluminum interconnects. So efficiency loss inside the panel, 3%, can't measure it. So you actually begin to unwind that whole corner that the solar panel design is in. And ultimately, what we're going to do is make that into a program that we can build here in Claremont. And one of the first steps of that is this paper that's going to happen in your physics department. So what we cover today, solar design system is very critical to safety today. And this is really important. I wrote on a flight down where they said, I don't care if your Note 7 has been updated or not, or if it's in the carry-on, or if it's in the overhead compartment, you need to turn it off. And tell us if you can't get to it, because we'll take it off. So you can't bring a Samsung Note 7 on a Southwest Airlines. Sadly, the reason it's catching fire isn't because it's on, but that's okay. The problem is in the public eye, lithium is so dangerous that now we can't do that. And that's right, sequel to the Sony debacle. Before that, the Apple Duo that caught fire, Teslas. And so lithium has a fundamental problem. It's made out of lithium and solvents. It's fundamentally flammable, so you're stuck with it. In solar, we're not. But today, the rest of the public doesn't know that. So it's very important that all of us that get involved with it, because we need this technology for carbon mitigation, really sweat these design details so that we don't end up with this idea that, hey, this causes a lot of fires. And with all the video that's available, just a few parts per million of these catastrophic events on the 6 o'clock news can really ruin our industry. So it's key. Fortunately, help is on the way. So we've kind of got a basic tool to engineer this problem out. And then with public policy, economics, which is being covered simultaneously in the next room, we're actually going to prototype this whole thing. An ultra-safe solar panel that can be manufactured in the community with nonprofit manufacturing economics for the right households that can be scalable. And then the idea is to then prove that out here and then step and repeat that across communities in California. Unless you think because that first thing has been thought through, this conductance idea, keep in mind nobody's designed solar cells for this kind of an environment. So the overdoped cell that may have significant shunting issues with an aluminum interconnect system that's all welded together, that cell doesn't exist because you couldn't make a panel for it today. A DSSC panel hasn't been made because the first time you had a shadow, you would devolve one of the cells, but now you can actually do that. So that's the solar cell technology that's being developed by the chemistry department here at Harvey Mudd. Dye-sensitized solar cell. Very, very sensitive to reverse bias, though. So there's a tremendous amount of opportunity to then take that basic principle, just like the law of photoelectricity, and then reimagine what the designs are. Even on the materials side, we use silicon nitride on solar cells today because of these well above 100 degrees C temperatures, but this is actually a vacuum deposited organic anti-reflective coating on my glasses. This would make a dramatic impact on how efficient the solar cells were and how inexpensive they were to manufacture. So it really changes the whole game up when solar cells become a low temp technology. Okay, so Claremont Locally Grown Power, Claremont Locally Grown Power is the program that's going on here. There are papers here that cover this empirical study that's going to be going on. Looks at how the solar installations can change, because now that the panels manage this off-axis thing, we can do multiple axis installations. I think the proof is here somewhere. It's a formally provable technology, data sheets, manuals, papers, and then of course lots of stuff available on the web. They are capturing this whole thing, and the presentation is going to get posted, but it's all available. You can communicate with any of your team members. If you want to be considered for an internship slot, I think they are just about to announce the job descriptions next week. And so there's opportunities to work on everything from lab work to community work on the other side, on the political side. And then just a short pitch. This is the first time I've actually done this at any university anywhere. Some of you people are going to end up being prolific inventors. This was my 61st patent, this FOZHS technology that prevents hotspots. I just realized in 2011 that we kind of have a choice about how we license our technology, where it gets manufactured, and we're the people that drive whether those middle-class manufacturing jobs happen here or in Shenzhen or in Delhi or in Germany. So this little paper that is one of the links is actually kind of a founding principle that occurred to me after 4 startups and having everything manufactured overseas, that we can make decisions as inventors that make a huge economic difference for everybody. So you don't need Congress, you don't need the consumer to go buy American. You, as an inventor, can control how your technology gets licensed and how you negotiate your employment. So take a look at that if that's helpful as you move out into industry. It only takes a few of us to make that decision, and then you look at any one product that has an invention in it, and all of the explosion of stuff that gets pulled into that product because of where that invention is. If it can be manufactured in the U.S., then that's going to pull everything towards it. And by the way, before you think I might be saying something that's unfair, this is actually a kind of an established policy in Japan. They tend to keep things for 11 years before they'll license it outside the country. It's also very common in China and in Germany. In the U.S., we're taught that the inventors don't have a role in that. So sorry for a little ad, but that's one of my particular causes, is to convince those of us that come up with this stuff that we can make a difference to the U.S. economy. Okay, well, that's it for today. So you've got all the contact information. You'll be able to have the slides. Even more stuff is available on the website. Any questions about any of this stuff?
So Lewis told us that you're looking for GIMC students to sort of build some of the technology that you have and test it and stuff like that. Do you know when that would start?
So I'm not directly involved in the recruiting process. I was in a conversation where they talked about starting that recruiting next week. I believe the job descriptions are already written. I don't know if they're approved or if they've been distributed.
Okay.
But Lewis will be able to tell you exactly what's going on. I think it's his thing. Well, and of course you.
That's right. So it should happen really in the next week or two. And you give emails.
Yeah, and the one that happens here, lots of fun. You get to reprove thermodynamics, and then this basic property of solar cells in a very, very step-by-step way. And then I'm hoping eventually we'll put some of your fantastic interferometry to work to actually show the devolution of the cells under these various conditions. Because interestingly enough, our industry's really studied these kinds of problems only in solar panels, never with the cells by themselves. And so a lot of literature exists where they took it apart after it had been in the field for a decade, but nobody ever saw it happen. They just saw the plane crash afterwards. And you'll be in a position to crash the plane in this particular set of experiments. Just get good at soldering, because you lose your sample when you do it.
Ken, would you mention I think you've had two generations of prototypes that you've been testing?
3.
So this is the third that you're heading towards, or have there been 3 generations?
So the electronics arguably is just about to be in its 4th. We only actually made one panel. I mean, we made several panels, but only one design, the quarter cell 80-20 configuration that you see here. And so while we've been waiting for this to get funded, we've been steadily simplifying it, reducing the component count, doing, what are called FMEA studies on it to ensure that there's no single point of critical failure. And so all that stuff standing on one foot and the other waiting for us to get underway. Having said that, the bypass diodes that are in a conventional solar panel box have more critical failure modes than the controller box does that we've already done. So some people call that polishing the apple, but we want it to be as low cost and easy to build as possible when we finally do get off the ground on this thing.
The controller box has a bunch of microcontrollers in it, or
Yeah. So it's based on PIC microcontrollers that have embedded ADDs. That's very, very inexpensive. What we really do is we break the panel into two pieces. So today, because of bypass technology, the panel is organized into three 10 up, 10 down segments. So 20 cells, 3 segments, vertically, which is a problem, right? Because the easiest way to carry a solar panel up and put it on the roof is vertically, which means, unfortunately, because shadows tend to be, sun's up there, this is down here, they tend to be cast across the entire bottom of the panel, and the dirt accumulates across the entire bottom of the panel. So that's actually a problem. You end up poisoning the whole panel's performance with a shading problem or a vent pipe or something. Ideal PVs are 80-20 horizontally strung because we can do it anywhere. We don't care how long the wires are because it's a high voltage internal system, so we don't have a wire length problem where we put the electronics. So the bottom part is 20% of it, and that has its own converter section, and then it shares some of the logic with the upper part that's 80%. And the idea is, if you've ever lived in snow country, you have something called a mud room. So when you come out, you're going to have stuff on your shoes, and it's just unavoidable. Well, if you're going to have shadows and you're going to have dirt, it's going to be on the bottom of the panel. So we designed the panel around that idea to optimize its output. But anyway, that controller uses zero current switching, a very, very high efficiency technique with no residual current in the inductors so that the controller doesn't stop the plasma arc from happening. The physics of volt-second balance in the inductors stop the plasma arc from happening. And it's controlled by the microcontrollers, which synthesize the response that the inverter sees. So the inverter sees, instead of a peak, it sees these things that look like pyramids. So any place along that line is optimal power. So what happens is if the panels are illuminated in different ways, you can match the current by taking the whole voltage of that section down. And that means you can have panels that are in multiple headings and stuff. So we basically used the fact that we're using microcontroller control to implement that wish list that you saw, so that from the inverter's point of view, it looks at the solar panel and says, man, that's perfect. Normally, an inverter has DC ripple on the link capacitor because in US, household current is single phase. So you need variable current. So that actually shows up in the panels and that dithers the maximum power point. The controller that we implemented is so fast that it actually tracks that. So the ripple never actually hits the cells. So one of the things that's going to happen after the little study that we're talking about in the lab is we're going to build these things out and do an A versus B test with conventional panels and these with vent pipes, and multiple headings outdoors, and then actually quantify what the yield gains really are. But we expect it's going to be very significant compared to conventional panels, because normally you can shut a conventional panel down with just one vent pipe. That's why when you look at a roof installation, you'll see there'll be like a whole gap where there could have been a panel, but there wasn't because there was one vent for, something, and it cast a shadow, and so no, we can't install a panel there. It might get a shadow. And they're obviously concerned about safety and reliability, but here we don't have that problem. So when you read the manual, you'll see there's an entire table that shows the difference in installation. So we're going to have a lot of fun upsetting the apple cart, not the least of which is those fires, because it's very easy to generate plasma arcs with conventional panels, and these won't do it. And it's very easy to generate hotspots, and these won't do it. You can imagine the fun we're going to have in the parking lot torturing conventional panels next to these and documenting the differences.
So do you have like a bunch of embedded systems engineers working on this project too? The ones that are implementing the...
No, it's just a bunch of old guys, but pretty good. My chief electrical engineer has 2 different smart meters under his belt. He's done all sorts of RF design and lots of power systems. I have maybe a dozen or so patents in power conversion and control systems. So we have a fellow whose main specialty is mathematics, so It's just a few people. It's really not that. Once you solve this problem, and now you don't have to worry about reverse bias anymore, then the other stuff is, just a few kilobytes of code in a little microcontroller. I mean, it's not that bad, and you guys will probably exceed us handily as you begin to get into more and more sophisticated implementations of the technique. But it's only a team of 5. And all of us are ex-startup people. This is the first time we're doing anything that's focused on public-private partnerships, that isn't venture finance, that isn't about overseas production, that is about job creation in the U.S. And so we're all attracted at this stage in our life to doing something that's going to make a difference.